All right, so here's a question that it gives you a Lewis structure, and it says, I want you to determine the hybridization of the atom, the molecular geometry, the bond angles around that atom, and the number of sigma and pi bonds around this particular atom. So it really means that not only do you have to draw Lewis structures, you have to be able to look at them and examine them and figure out what's going on. And so if you have a lot of practice with Lewis structures, this should be pretty straightforward, but we do want to show you a different way of looking at things. For instance, this one is not drawn by hand. This one is drawn with software. So it's just going to be slightly different than the other things that you look at. But everything else goes exactly the same way. So let's start off with this first one, this first nitrogen. So let's take a look at this guy. All right, so the first thing is to figure out the molecular geometry. Remember, the molecular geometry is not the electron geometry. The molecular geometry is the shape of the molecule, only including the bonds. But in order to know the molecular geometry, it is helpful to figure out the electron geometry, because maybe that's the way that you learned it. And so let's take a look at the first one and let's count the number of geometry groups. I've got one bond to the carbon, another double bond to a carbon, and I have a lone pair. So that's 3 geometry groups. 3 geometry groups is trigonal planar electron geometry. And trigonal planar electron geometry with one lone pair is bent molecular geometry. Okay, so if it's trigonal planar molecular geometry, that's what we use to figure out the hybridization. That means it's sp2 hybridized. What would be the bond angles in a trigonal planar molecular geometry? 120 degrees. So you still really do need to know the electron geometry in order to situate yourself with these other questions that the problem is asking you to answer. All right, the last one is number of sigma and number of pi bonds around that particular atom. Well, it's got a single bond and a double bond. So that means the single bond has a sigma bond and the double bond has 1 sigma bond. So that's a total of 2 sigma bonds. And the other bond in the double bond is a pi bond. So it's 2 sigma, 1 pi. Okay, so let's take a look at the next one. The next one is this guy. Its electron geometry is based on 4 geometry groups, 3 bond and a lone pair, so it's tetrahedral. But with the lone pair, that tetrahedral electron geometry becomes trigonal, pyramidal, molecular geometry. The hybridization is based on that same electron geometry of tetrahedral. So it's sp3. So are the bond angles. So it's 109.5 degrees. And then I only have single bonds. So there's 3 sigma bonds and 0 pi bonds. What about this oxygen? The oxygen has 4 geometry groups as well. So it's trigonal. So excuse me, it's tetrahedral parent electron geometry, but because it has 2 lone pairs, the molecular geometry is bent. So again, tetrahedral electron geometry, 2 lone pairs is bent molecular geometry. The tetrahedral parent geometry gets you sp3 hybridization. It also gets you 109.5 degree bond angles, and there's only 2 single bonds, so it's 2 sigma, 0 pi. And finally, the last one, that's this carbon here. This carbon is got 2 geometry groups, a bond on either side. So that is a linear electron geometry, and with no lone pairs, the molecular geometry is the same. It is sp hybridized. I can determine that based on that molecular geometry, or excuse me, I can determine that based on the electron geometry. I'm going to go back here, spell this correctly. Linear. All right, and now let's figure out the bond angles. Well, if it's linear, then that means the bond angles are 180 degrees. Now, it has a single bond and a triple bond. So the single bond contributes 1 sigma bond, and the triple bond contributes 1 sigma bond. The other 2 bonds in this triple bond are considered to be pi bonds. So you get linear geometry, sp hybridization, 180-degree bond angles, 2 sigma and 2 pi for that last atom. Okay, that's that.